everyone. I am Dr. Pauline Fu. In this video, I will present normal probability distribution. Topic include use uniform probability distribution, graph normal curve, state the properties of normal probability distribution, explain the role of area in the normal density function. Let's look at the uniform probability distribution first by taking a look at an example. Suppose that the United Parcel Services is supposed to deliver a package to your front door, and arrival time is somewhere between 10 a.m. and 11 a.m. Let the random variable x represent the time from 10 a.m. when the delivery is supposed to take place. The delivery could be at 10 a.m. or at 11 a.m. When the delivery at 10 a.m., we set the random variable 0 because that is the time to start delivery. And when it is at 11 a.m., the random variable x equal to 60. With all 1 minute interval of times between x and 0 and x equal to 60, equally likely. So let's repeat this sentence from here. Let the random variable x represent the time from 10 a.m. when the delivery is supposed to take place. The delivery could be at 10 a.m. with all 1 minute interval of times between x equal to 0 and x equal to 60. That is to say, your package is just as likely to arrive between 10:15 and 10:16 as it is to arrive between 10:40 and 10:41. The random variable x can be any value in the interval from 0 to 60. So x is between 0 to 60. The unit is minutes because we are observing 1 hour. From 10 a.m. to 11 a.m., that is 1 hour, 60 minutes. Because any two intervals of equal length between 0 and 60 inclusive are equally likely, the random variable x is said to follow uniform probability distribution. So uniform probability distribution means whatever x is, the probability of x is the same. Even you have different x, but the probability of those different x are the same. That is the uniform probability distribution. Next, let's introduce a terminology. Probability density function. It is an equation used to compute the probabilities of continuous random variables. It must satisfy the following two criteria. Criteria 1, the total area under the graph of the equation over all possible values of the random variable must equal to 1. Criteria 2, the height of the graph of the equation must be greater than or equal to 0 for all possible values of random variables. Well, now let's look at the example we gave you before, okay? Delivering parcel. And this graph illustrates the properties for the time examples we gave you before. So the area of this rectangular, okay, equal to 1y, because the area of rectangle is the height times width. The height is 1/60. Why it is 1/60? Remember, the height represents the probability. Okay, the probability is 1/60 because you have 60 minutes from 10 a.m. to 11 a.m. Okay, the probability of each minute you are going to get a parcel is the same, 1/60. That is probability. And over this direction, this x equal to 60. Again, because it is from 10 a.m. to 11 a.m. You have 60 minutes. Okay, that is the random variable x. So let's check the two criteria. One, the area is equal to 1. So the rectangular area height times width equal to 1. The second criteria, any probability is greater than 0 here. The height of the graph greater than or equal to 0. The height of this graph here. So it satisfies the properties here. Okay. The values of random variable x less than 0 or greater than 60 are impossible. Okay. Because you restrict the delivery time from 10 a.m. to 11 a.m. Not before 10 a.m., not after 11 a.m. Thus, the function value must be 0 for x less than 0 or greater than 60. So if it is before 10 a.m., this function equal to 0. If it is after 11 a.m., the function equal to 0. Okay. The area under the graph of density function over an interval represents the probability of observing a value of the random variable in that interval. Okay. So let's look at this example. Area as a probability. So the probability of choosing a time that is between 15 and 30 minutes after the hour, means after 10 a.m., is the area under the uniform density function. So remember, this is 10 a.m., this is 11 a.m. Okay. So the probability of choosing a time that is between 10:15 and 10:30 okay, is the area of this rectangle. So the probability of between 15 and 30 is, so how do we calculate the area? The area of this rectangle height, the height is 1/60. This is the height, 1/60. And the width is 30 minus 15. 30 minus 15 is the width. Okay. 30 minus 15. So you get 15 over 60. It is 0.25. So that is the uniform probability distribution. It is usually a shape of rectangle. Next, let's talk about normal curve. Remember, if you have a large data set, the relative frequency histograms usually is symmetric and bell-shaped. So if you have this symmetric bell-shaped, we call that is the normal curve. A continuous random variable is normally distributed or has a normal probability distribution if its relative frequency histogram of the random variable has the shape of the normal curve. Normal curve means bell-shaped symmetry. So this curve is a normal curve, okay? And this center point is population mu. Sigma is population standard deviation. And this point represents mu plus 1 standard deviation. And this point mu minus 1 standard deviation. And the curve corresponding to 1 standard deviation, the point, there are 2 points on the curve corresponding to 1 standard deviation. And those 2 points we call inflection point. Okay, inflection point. Why they're called inflection point? Because from this point, it is from concave up to concave down. If you study calculus, you know the slope is changed, the sign. This graph shows when you have the same standard deviation, but different population mean. The red graph, this graph, shows when you have population mean is 0, mu equal to 0. Standard deviation is 1. And this blue graph shows mean is 3, standard deviation is 1. So what is the difference between those two distributions? The difference is they have different population mean. The red one has population mean is 0. The blue one, population mean is 3. And what is the similarity between those two graphs? They have the same standard deviation, means the spread is the same for those two distributions, but the mean is different. Now let's look at this graph, the bottom one. If you look at this red curve, red normal curve, okay, it has the mean is 0. Standard deviation is 1. By the way, we call mean 0, standard deviation 1, that is the standard normal distribution. Okay. So let's look at the blue graph. Blue graph, you have the same mean is 0, but standard deviation is 2. Means the blue graph are more spread than the red graph. That's why the blue one has 2 standard deviation. The blue one has 1 as standard deviation, but they have the same population mean, both equal to 0. So as you can see from this graph, the standard deviation measures the spread of the data. The bigger the standard deviation, the more spread. The smaller the standard deviation, the more data concentrated. So now let's look at the properties of normal density curve. It is symmetry about it is mean, mu. See, this is mu. Okay, it is symmetry about the mu. Number 2, because in normal curve we have mean equal to median equal to mode, the curve has a single peak and the highest point happened at x equal to mu. So which one is highest point? When x equal to mu, it is highest point. And this point is the highest point when x equal to mu. Okay. And here is the highest point when x equal to mu. Highest point when x equal to mu. Okay. So this is the second one. The third one, it has inflection point at mu plus 1 sigma, mu minus sigma. Okay, inflection point. Remember here, at mu plus sigma and mu minus sigma, you have inflection point. Number 4, the area under bell-shaped curve is 1. So the area from here to here, this area equal to 1. Similarly, this area equal to 1. Okay. Number 5, the area under the curve to the right of mu equals to area under the curve to the left of the mu, which equal to 0.5 or 1/2. So maybe this one, take this one here. So this area, the area to the left of the mu. This area is area to the left of the mu equal to 0.5. And this area is to the right of the mu. This area to the right of the mu also equal to 0.5. Number 6, as x increases without a bound, when x gets bigger and bigger, the graph approaches but never reach the horizontal axis. So when x increase, but will never touch x-axis. It is increasing but never touch x-axis when x increase. As x decrease without a boundary, the graph approaches but never reach the horizontal axis. When x is decreasing, but will never touch x-axis, never touch. Okay. Number 7, the empirical rule, approximately 68% of the area under the normal curve is within 1 standard deviation. Approximately 95% of the area is between 2 standard deviations. Approximately 99.7% of the area between 3 standard deviations. That is the empirical rule, as explained in this graph. Okay. So 68% within 1 standard deviation. Okay. 95% within 2 standard deviations. 99.7% within 3 standard deviations. 3 standard deviations. All right, example. A normal random variable. The data on the next slide represent the heights in inches of a random sample of 52-year-old males. Question 1. Draw a histogram of the data using a lower class limit of first class equal to 31.5 and class weights is 1. Question B. Do you think the variable height of 2-year-old males is normally distributed? So this is the raw data. There are 50 of them. It is the height of 2-year-old males. The unit is inch. Okay. So to construct the histogram, you can use Excel, punch in those data, and then you go either data analysis, quick histogram, or you go to insert graph. There's an option for histogram that is only available for Office 365. If you have older version of Excel, insert graph does not provide histogram. Okay? So suppose this is the graph we get from Excel or other technology. Okay, this is the histograph. This is question A, create a histograph. And question 2, if this a bell-shaped normal distribution looks like it is a bell-shaped normal distribution. So I will explain this one here again. This is the area under a normal curve. Suppose that a random variable x is normally distributed with mean is mu, standard deviation sigma. The area under the normal curve for any interval values of random variable x represent either the proportion of the population with the characteristic described by the interval, or the probability that a random selected individual from population will have the characteristic described by the interval of values. So what does this statement mean? This statement means this is bell-shaped curve. Okay. The area, for example, this area has two interpretations. One, it is the proportion of populations, okay, with the characteristics, some characteristics. Wait, the sound broke. Nice. The second interpretation, it is the probability of individual from population will have the characteristics. For example, during a test, the mean value is 63. Okay. The mean value is 63. And this area, suppose, is 0.2. 0.2. And suppose this value is 47, just suppose. Okay. So for our test result, the mean is 63, okay? And this point is 47. This area is 0.2. So how do you interpret this 0.2? First interpretation, the proportion of the population of students whose mark lower than 47 is 0.2, or 20% of the students, their test mark is equal or lower than 43 or 47. That is one interpretation. The second interpretation, okay, the probability of students whose test mark is equal or lower than 47 is 0.2. So that is the area under a normal curve has two interpretations. Okay. So let's take a look at the example. Interpreting the area under normal curve, the weight of giraffes are approximately normal distributed with the mean 2,200 pounds and the standard deviation 200 pounds. Question 1, draw a normal curve with the parameters labeled. Question 2, shade the area under the normal curve to the left at x equal to 2,100 pounds. Number 3, suppose the area under the normal curve to the left of x equal to 2,100 pounds is 0.3085. Provide two interpretations of these results. So let's maybe I can draw the graph here. Let's answer question A. Draw a normal curve. So bell-shaped symmetry with the parameters labeled. Okay, so this is the mean mu equal to 2,200, sigma equal to 200. Okay. And this, for example, inflection point. So this point represents mu plus sigma, one standard deviation. And this point represents mu minus sigma. So this is question 1A. Question B, shade the area to the left of x equal to 2,100. So maybe 2,100 is here. This point is 2,100. And shade this area to the left. So this is the area to the left of 2,100. So this is question B. And question C. Suppose the area to the left of 2,100, suppose this area equal to 0.3085. Provide two interpretations. So interpretation one, the proportion of the population. Okay, the proportion of the population, the weight is equal or lower than 2,100 is 0.30 or 30% or 31%. 31% of the population has the weight equal or lower than 2,100 pounds. That is interpretation one. Interpretation two, the probability. The probability of randomly selected gerard whose weight is equal or lower than 2,100 is 0.3085. So that is the interpretation. And this also provides the solution. I already did this. All right. So in summary, what we did this video, we start off by introducing uniform distribution. It is in the shape of rectangle. Then we describe normal distribution, the bell-shaped curve. Okay. And we also give interpretations of the area under bell-shaped curve. Hope you learned something from this video. Thank you so much for your time. I look forward to see you in next video.